Development of a climate model is a very complicated process, right? So first, we have to understand the process, like physical, chemical, biological principle, which we want to formulate from experiments and observation mostly. And then we have to approximate that in equations, parameterization, like. Then we numerically solve it, make a model and numerically solve it. The model will give some results, and that will go to the validation process, and several validations, several try and error, and adding more components, experiments, we produce results. And if in basically in climate model, it's not about a single model. So various organizations like in USA, Canada, India, UK, they all have their own models, which they develop on their own. And these are all data, like this is called climate model intercomparison project. It is also monitored by the WCRP, another wing of UN only. So they have a repository of this model data set, and we have to intercompare models. If many models are agreeing with the same, like it is going to increase or it is going to decrease like that, then we have to believe that. So that's how these assessment reports are made, and that's how it is the working process, the process of this model set. Like once the model is developed, it is for the future perspective, right? So basically in a global climate model, it is a global climate model. Of course, as the name suggests, it simulates the values over grid points all over the globe. So there are other sections like regional climate model, like which we can work only over a smaller region of interest, like India or in South Asia, this kind of domain. So there is another set of experience for that. So basically a global climate model is a complex mathematical representation of the major climate components. And the primary component is of course the atmosphere. And it also, and of course the atmosphere is not a standalone layer, right? It is influenced by the ocean, wherein it gets touch in contact with the ocean. It is influenced by the land surface. It is influenced by the sea ice, especially in the poles and all. So in climate model, what we care about is the energy balance between these components. And its energy balance between the four components is the key to long-term climate prediction. With this information, like first process is to generate the scenarios or conceptualize the scenarios and make forcing according to that, and that's how the climate model simulates. So this is quite scientific. Like I just want to introduce the process, right? So there are some conservation of momentum, conservation of energy, conservation of mass. This is common for both weather and climate model. These are the governing equation, and these are very complicated equation. This is non-linear, and we can't analytically solve it. So we solve it numerically by grid, and it is a lot of computation, more than like right now the fastest supercomputers are used to for this weather or climate uses. Right? So this is how complicated the system is. So one thing I want to highlight is that last year was very impressive for the climate science community, because two of the pioneers of this climate modeling, Sikuro Manabe and Dr. Klaus Hasselmann, they were awarded Nobel Prize in Physics for their contribution in this climate modeling. So their work basically started all these things. While at that time, it's 1960s, 1990s. This is the time period which they started thinking of making a model which can simulate a long-term climate change and conceptualization, experimentation. So we are all following their startup. So now let me come to the interest of this topic. Like how AML can support numerical models. Right? So basically in numerical models, what's happening is that we have some inputs that may be forcing file or scenario file or whatever, like the observation, like that. Then it will be passed on to the numerical model. Each model has dynamics. Dynamics contain the solvers, like how to solve this and what will be the resolution of the grid, which we want to take, like information like that, and physics, like the parameterizations of various processes. So, and that will generate some output in terms of prediction. If it is a weather model or a short-term model, it will be predictions or forecast. And if it is a climate model, that is basically projections. We can't say projections may happen in the future. So these are just alternate situation or scenarios that may arise, right, which will be simulated by the climate. But what we do in AAML is that if we have an input data and a target data, we can generate models out of it in terms of weights and bias. Like we are using a convolution neural network, that information will be learned in terms of feature maps or representation power. Then, like these are a very, even a simple ANN is a very good function approximator. So this is the potential that AML has. So, and one limitation is that to train an AML model to its best performance level, we need a lot of data. So luckily, right now, the climate change is a big data. It's in the big data process, because a lot of data is generated from various sources like satellite observation, like ground observation, satellite observation, then model simulation, like that. Basically, it's called to be to some system to termed as a big data domain. It should be have these 6 values, like value, volume, velocity, velocity. The data should be accompanied by this kind of things. So climate data sets have large volume of data. The velocity, like the more and more data is coming into the picture day by day, and we have a variety of sources. And of course, we can, like, data has its own problem, right? But that's the best chance we have. So it is versatile also. And so, like, this diagram is basically taken from a review paper by Ristein et al. In 2019. The big data challenges in the geoscientific constant. So one thing I want to highlight is that, so this to tell knowledge from data, data from knowledge. So if we have data, we can train this neural network, simply speaking, to gain knowledge, like what is the relation between these two variables or these two phenomena, like that. Such information can be retrieved, and that can be used to further improvise or generate new set of data. So knowledge from data, data from science, data from knowledge. So this is also, this diagram is also taken from the same Ristein et al.'s paper in Nature. So basically, in a classical machine learning task that can be classified into, like, there are many tasks which is just for your understanding, that's simply like we all use this Google Translate. We give in one language, it translates in our own language, some other language. And we have this text to speech, like audio from our audio, it takes actions, these kind of things. There are all many actions. So some of the things which is like, these are some analogs which can be used in the Earth system modeling task. So the one is the object classification and localization. In here, you can see one diagram. That is a cat and a dog. So the model, the AML model is predicting that 0.9 probability is that it is a cat and it is a dog. So similarly, if we take a global model simulation as a whole, each time step is an image, right? So from each image, there are, like, this is a circulation pattern. So some circulation causes some extreme events. So this, you can see some tails over here, like, which is basically the atmospheric rivers. Then a tropical cyclone has a spatial structure. So from long-term climate data sets or like that, if some information can be read, like this is a potential analog application. Another one is downscaling. So Basically, these global climate models are run at 100-kilometer resolution, but 100 kilometers is a long distance, and if you want to increase the resolution, that requires more computation. Even though scientists are doing, like many agencies are doing such hard experiments, it is very computationally expensive. So, like this is from data we can make AML model. We can downscale using image super resolution. This downscaling is similar to the super resolution task in classical machine learning. Then another one is the next frame prediction, like video prediction. So same, the time, like short term forecast can be like the time evolving things can be trained from data, and that can be used as a model. Then language translation. This is simply time series translation. So the dynamic time series modeling, like these are some, just for example, I'm showing it to you. So these are a few of the things which I am working on, but still this AML provides novel and powerful ways of accurately and efficiently recognizing complex patterns, simulating nonlinear dynamics, and predicting the spatio-temporal evolution of weather and climate process. But AML algorithms, however, do not necessarily obey the fundamental governing laws of physical system, nor do they generalize well to scenarios on which they have not been trained. So there are some, even though it has a lot of potential, there are some limitations. So one of the most limitation is that it is very sensitive to the data, and data is not always perfect. There is always uncertainties in the data or the data processing things. So this all influence our results. So even though it predicts good, AML can predict things, it may not sometimes follow the general physical law. Like a model which can be trained to predict the precipitation over the next 10 days. What if it gives a value like -10? So there is no physical meaning to that, right? So precipitation should be always be some positive value. So this kind of information is like it is very sensitive to data. So that's how this new domain like physics informed machine learning evolved. So how can we incorporate physics constraints and existing domain knowledge into AML algorithm? So I'm not going into deep. There are several applications for the PAML, such as emulation of processes, scaling, forecasting. So what I talked until now is very related to my expertise, but AML can provide much more solutions to environmental issues. So in this third section of this talk, I would like to introduce, like, I'm not an expert or give some guided idea like that, but I would like to share a few ideas with you. So I hope most of the listeners are from the engineering background. So basically in future, the engineering sector has a lot of, engineers can contribute a lot using this AI for environmental sustainability. So this is only, whatever I talked is just a one part or one bullet point in this entire flow diagram. Right? So basically, we can focus on making clean power, like renewable source of energy, smart transport options, sustainable production and consumption, sustainable land use, these kind of things, like where AML techniques can be implemented. There are a lot of scopes and holes which we need to address, which can be addressed, like in biodiversity and conservation, healthy oceans, water security, clean air, like that. So there are many options like that. So there is this concept of adaptation, and it's not concept, like when the change is inevitable and it's a part of life, we have to adapt to the changed scenarios. Like in future, suppose the flood events will occur very frequently, but we can't do anything because it's too late. Then what can do is to adapt to that scenario. Then we can make buildings which is resilient to this flood events like that, right? Then training system. So many things can be implemented like that. So another option is the mitigation. This clean power, like reducing the emission is contributing to the mitigation, which simply means that if we mitigate the emission, we can stop the climate change. So right now we can focus on that because it's not too late, but it's not too early as because we are right in the middle of nowhere. So many applications are there which the engineer sector, the science sector, all can together contribute to the issue. So like the topic of this section I titled this as the opportunities and constraints, right? So AI has a footprint, carbon footprint. That's another issue because training and AML takes a lot of energy, which has a carbon. So this is one news excerpt which I took from last year's Stanford news. So basically, it requires a lot of energy, and energy is not always renewable. So like that, directly or indirectly, it has some footprint. So that's one constraint, like how hard we can do this thing continuously. If someone say the disease itself is the cure to the disease, there is no meaning to that, right? So there is some new study from Google which say that AI's carbon footprint is big, but easy to reduce. So there are some constraints like that. So we have to like in the energy sector, in the planning sector, in the architecture sector, everywhere this AI can be used. So it's not mandatory use it everywhere because but without AI also many things can be done. But AI has a potential that sometimes if humans miss something, this AI can guide us. Like there is a scope like that. So just we have to find out how and where. So this will all be a collective effort. And that's all I wanted to share with you in this talk. So thank you. And thank you for inviting for me this talk. And special thanks to the Department of Electronics and Communication, Research and Technology, and Prime Minister's Research Fellow Scheme for funding my PhD, and CGMM and Department of IISER Bhopal for hosting my PhD research. So, and if you have any questions, I'll be happy to answer.
Anybody want to ask any question? Participants, do you want to ask any question? So I think, thank you, Midhun sir. Thank